It's time to start next session, but the presenter is still preparing out of the room. Let me call him. And before starting next session, there is an announcement. We will take a group photo on the first floor, ground floor. So in coffee break time, please kindly gather at the first floor. If you want to join the group photo, please go to first floor. Thank you. 大丈夫ですか？と XGA の 60Hz で出していただけると助かります。今一瞬映った。
Okay.
The next session, the presentation is, as you see, Let Python Talk Native by Moriyoshi Koizumi. Please.
Thank you for coming to my presentation. I'm going to talk about the foreign function interface in Python. That means around the world. And those tend to have different API conventions where some library utilizes return value as the means of reporting errors in the library. But the other library may use exceptions to report erroneous status in the library or communication between the library and the OS functionality. So we often need to use library-specific tweaks to cope with the differences between the libraries. And it tends to be cumbersome. So, okay. FFI is required. And then, what is, first I want to explain what is FFI and what is, FFI stands for Foreign Function Interface, and the term is initially coined by Common Lisp community in the specification. That is actually a mechanism or, say, a facility for a programming language to interface with another programming language. And usually, the programming language that utilizes the FFI is called a host language, and the programming language used to implement the library is called a guest language. In almost all the case, FFI involves a bunch of wrappers. A wrapper is a function that wraps a function call to the library, and it converts the types of the arguments that were passed from the host language to the types of the guest language, and for the return value, vice versa. Next, I want to explain about API and ABI. API is a high-level interface to the library from the user point of view. Yeah. It's just kind of it comprises method signatures and return value convention, error handling, and object ownership. Method signatures are those, just like prototype definition in the C and C++ headers. And object ownership object ownership is object ownership needs to be cared when you use C++. Mostly want to use C++ libraries or sometimes C libraries that are whose APIs are object-oriented. And the objects are sometimes reference counted in the library or just a bare pointer. The ownership of which is opaque or kind of weak reference, or the library may use smart pointers that is actually reference counted behind the scene. And the ABI. ABI stands for Application Binary Interface. Those define the calling convention to the library. A calling convention specifies specifies how the function in binary level is called, needs to be called to correctly get the callee to work. There are many kinds of calling conventions. These are x86 calling. These are part of x86 calling conventions. There are many, and sometimes you need to care about alignments. Alignments are how a data structure is represented in memory, how the fields of a structure is organized or laid out in the memory. They can be packed structure or word aligned. This diagram represents a function call to the standard C library function, and this function takes two arguments, and the first the diagram also describes the first argument, the pointer to the string literal will be stored into the CPU register called RDI, And the second argument will be stored into the register RSI. And then the actual library function is called, and the library function receives the value from the registers which have been just populated, and then do the work. Yeah. And about the wrappers, there are two kinds of wrappers. One is precompiled, and the other is runtime. Precompiled wrappers needs compilation, while runtime wrappers don't. That means precompiled wrappers have usually source codes for the wrapper, and the source code needed to be compiled in compile time, along with the Python scripts or other C codes that makes use of the wrapper. In the other hand, runtime wrappers are created dynamically during running the Python script in question, and it's because of its dynamic nature, it runs usually slower than the precompiled wrappers. Okay, so let's talk about the FFI implementation that are popular in Python. Yeah. The first stuff is Swig. Maybe you have heard that name because of its long-standing history. It actually started developing in 1990s, late maybe 1996 or so. And so its interface and usage is very stable in comparison with other FFA implementation. It utilizes a file called interface definition file that describes the interface between the library and the host language. And thanks to the syntax of the interface definition language, the same interface file can be used for multiple host languages, and that is yeah. So Swig is general purpose FFI, and it's not bound to Python specific things. And various kinds of API patterns, yeah, like what I explained, error handling and exception handling, or object ownership and so on are supported. But the interface definition language consists of many directives, those which are kind of a bit peculiar, and those tend to be hard to learn. Yeah, this is tiny C++ code, and when this is made of two classes. One is foo, that has a method that returns a pointer to bar class. And bar is just a simple class that only has a constructor and a destructor. And you need to just 6 lines of interface definition file for the swig. And then write a setup.py, and it works. It's very easy. And in addition to those, Swig is natively supported in dist utils, so you don't need to install or prepare external packages. Okay, then move to ctypes. Ctypes is runtime FFI in contrast to Swig, that is precompiled type of FFI. Ctypes makes use of libFFI. That is a C library that handles dynamic generation of wrappers and more. And ctypes module is bundled with Python and can be used out of the box. So you completely don't need to don't even need to write a setup.py, and just simple script works. But it doesn't have any good C++ support. So if you want to C++ library with ctypes, then you need to learn about C++ AB first, and then we'll need to write platform-specific or architectural-specific code with gory details. This is an example of ctypes. You need to specify the argument types and return types for the function. But it works after the function, after the wrapper is created. Okay, then I'm going to talk about cffi. cffi is relatively new library that is developed by a number of developers who are involved in PyPy, and it actually features supports for both PyPy and CPython, and also utilizes libFFI in the same way as ctypes, but it's much easier to use than ctypes because you can define runtime wrappers with a strings of C-like expressions like this. The third line of code wrappers for put function that comes from standard C library, and then the wrapper can be used straightforward just like ctypes. But it doesn't have any good C++ support either. So the same thing applies to the module as well. And then Cython. Cython is not really a facility that generates a wrapper, but it actually enables developers to write wrappers in a very easy manner. Because it allows to interleave Python code seamlessly with the guest language specific code. When you need to work with C++ library that contains methods of overload that are overloaded, then Cython may not well handle those because the interface from the the interface is the interface needs to be written in Pythonic manner where no functional overloading is considered. So you need to just inspect the types of the arguments and then branches to the right code when you support such overloaded functions. And it generates enigmatic generator wrappers. That is very hard to read. And when you when it gets wrong, it's quite hard to debug. Okay. Yeah, this is the code that is generated by Cython. I hardly think I can read those code. It actually intended to be read by a C compiler and not by human. And Boost.Python. Boost.Python is a part of the library suite called Boost. Boost is a C++ library suite that consists of 30 and 40 kinds of libraries, including threading and math and everything. And Boost.Python is kind of similar to Cython because you need to write wrapper code sometimes because Boost.Python actually helps developers to determine Python side of the interface and does not automatically generate wrappers. But the interface definition can be written in plain C++ code in contrast to Swig or other, in contrast to Cython and Swig. So it's rather easier to learn, I think. And first of all, it fully supports C++ RTTI. RTTI stands for Runtime Type Information. And it actually matters when you use C++ libraries that utilize many kinds of classes, many classes, and some of those classes have many levels of inheritance and kind of many levels of inheritances, and the part of the methods of the classes are virtual functions, where the implementation of the object. Which implementation of the method is determined when it gets called, when its object's called. And so when you want to use RTTI feature of C++ with Cython and other FFI implementations, then you may need to write your own dispatching wrapper. But Boost.Python actually automates it, and maybe you won't need to write your code in many cases. And it supports functional overloading. It is very good thing because many existing C++ libraries makes use of the feature. And the library Boost.Python is actually a collection of tiny utilities that which can be used when you want to just simple Python extension. So it can be well integrated with the existing cffi code. This is the wrapper for the library I presented presented as a swig example, and it's very simple. You need to write. Boost.Python include at the top of the file, and then write Boost.Python module magic macro. Then put the module name in the parentheses, and then the class, a magic class defines the wrapper for the corresponding C++ class. And you will also need to put def method for each of the methods that are public to the users in the library. In this example, the only public method is foo. So I just put one def definition right after the constructor of the class. And the class is actually a templated class, and it accepts the underlying C++ class as the parameter. And the and def method accepts pointer to the function as the second argument, and the third argument specifies how the pointer to the object needs to be managed in the Python side. In this example, a newly created bar instance will be returned from foo methods. So we want it to be managed in Python, managed by the wrapper of the bar class, and because it needs to be destroyed and freed when the bar wrapper is garbage collected in Python side. So I specify the return value policy to the method as well. And the policy is specified the template argument of the return value policy function. On the other hand, we need to specify new object. We need to specify new object directive in Swig's interface file to get it managed by the Python wrapper. Without those, the pointer to the C++ object will be kind of opaque, and a memory leak can happen. So this is very important. This is the Cython file that describes the wrapper for the library I have just shown. It actually looks familiar because the most of the syntax resembles Python, but at the nature of Cython, you need to write the same definition as the C++ header file, the Cython file, and write wrapper functions for write a wrapper function for each method of the C++ class. That is not good for a larger library. But the Cython will be found useful when you need to write a complex wrapper where the library's memory management is very complicated. Because Cython's file is kind of very verbose and verbatim. So the other developer can read the file easily. And can be maintained easily, I guess. Okay. I guess I have almost explained what I wanted to what I wanted to do in the talk. So, any questions for those?
Any questions or comments?
Thank you for explaining the FFI. I'm interested in Swig because Swig supports many languages. So, point of view from library developer, many as language support is good to reduce the development effort to bridge the language. But from a user side, stability. API stability or ABS stability is needed. So I'm confused that which framework or which tool is best for bridge Python.
Okay. Maybe it's not a good thing to conclude it as case by case. From my experience, if the library is quite simple, and the memory management is easier to understand, then both Swig and Boost.Python will fit to such libraries. But if the library is quite complex, and you need to take care about the life cycle of the object, then you may want to use Cython as well.
Thank you very much.
I have many questions to. You are showing a very good listing or lot of many interfaces, but no conclusion. So my simple question is: overloading, function overloading, meaning or linking a function by name, dynamic loading, or
Sorry?
function overloading.
Yeah.
Several times you are showing what is overloading.
Okay. Function overloading is when there are several functions that have exactly the same name, but the argument types for those are different.
C++ or the
Yeah.
okay.
Then those
Argument
functions-
dependency or it's a change to a dynamic loading. Yeah, in some cases of this code, okay. And the second is you are showing it to a no good C++, no good, but C++ is a big, huge functionality. So it's not good, no or not good, or what meaning is no good? Completely, you need to completely C++ linking or possibility. C++ is a very huge implementation, so or some compiler has a different result. So you trying to ask no good. What is a no good in your presentation here today?
It's how to say?
So how four times to show you no good C++ interface linking.
My conclusion will not blame C++ and its complexity, but rather how we can tackle with the libraries that are written in C++ and in Python. So, and I just presented the possibility. In other words, ways of dealing with the real-world problems when you work with the libraries. So, okay. So then, what is your point regarding those?
ノーグッド、その C++ ポートがノーグッドだって言ってるのはどういうポイントがノーグッドなのかと。例えばその ctypes がファンクションネームをマングリングするとかそういうようなお話ですか。
Yeah, I didn't say it's not good, but ctypes and cffi don't support C++ natively, so you cannot use them out of the box.
It's no functionality or some point okay, some point good bad. Completely no. Or
You can actually use them for interfacing with C++ functions, but you need to do some kinds of hack that may contain details of architectures and platform specific stuff.
I'm just wondering, so this whole talk is about talking to C from Python and the other way around, right? What if you want to talk to, I don't know, Node.js or Ruby? Would any of these options be a good option, or do you recommend something else?
When you want to interface with the other scripting languages, I guess there are two viable options. One is to use a kind of remote procedure calls to interface with the guest language, and that usually results in stable. Because the runtimes are isolated, so they don't interact with each other in a bad manner. And the second option is to use the cffi that is provided by the guest language, and then makes use of those functions to call to a method in the guest language and vice versa. But it tends to be unstable because the strategy for the memory management can be different between those languages. For example, Python uses reference-counted garbage collection, whereas Ruby uses mac and sweep.
Okay, we may have more details, more in-detail discussion on the way to take a photo. So we'd like to close this session. Thank you very much.
Thank you.